If you are ever interested in a good time, look up at how high viewership is on these videos. It's kind of weird. But that's not true. I do know who's watching it. So, you don't all know this. People from around the world email me asking why Jimmy's lectures aren't on the YouTube channel. Because they're like, yeah, so we've been watching your lectures, but everyone kind of wants to see Jimmy's lectures. And I was like, you haven't seen them. How do you know you like them? Right? So I don't know what's going on. Like, yeah, maybe like paywall them. I don't know how in demand they are, right? Like I told, like if I ever get an email, I guess maybe I told you this privately, but like if someone ever reaches out to me and like any of you are my students, be like, hey, we want to see this student's work, I'll be like, oh yeah, that'll be $700, and then I'll give you the money. Okay, that is my promise I'll make to you.
This is when you decide to say this after you start streaming.
Yeah, of course. No, I'm allowed to sell your work.
Oh.
It's my work that is GPL v3 licensed. I don't know what license you use for. Oh, have any of you heard of the unlicensed? I was using some code that was under the unlicensed the other day. Yeah, I didn't like that one very much. Okay, welcome back. You should have a working breakpoint handler and double fault handler. Is that correct? Did I make that up? Am I telling lies? No, you definitely should have that. That was assigned like 10 years ago. Wait, is there supposed to be stuff here? Oh. No? Yes? Double. Was there like not homework last week? That's right. That's right. Oh, okay. That probably puts a ceiling on how many classes we can cancel, huh? I don't want you to like graduate and then someone asks you what you did in this class and you're like, well, obviously we watched the movie, and then there was the bridal shower, and then there was SSRD, and then we had spring break, and then there was King Day, and then there was... That's all of them. Okay, that's not
It's called operating systems, so that has to count for something.
The class is called operating systems. Okay, so yes, that should be extremely done. Okay. I like hardware interrupts a lot, and I like hardware interrupts a lot because they add this layer of complexity that would otherwise not exist in computing systems, where there's sort of, that's not true, it could exist. It would be difficult otherwise to justify things that are asynchronous. You could also argue this convincingly from the network's perspective, that like, oh, hey, there's some other computer on a network somewhere and you don't know how long it's going to take to do something. You have to be ready whenever it happens. When some of you were discussing graduate school, a real thing that some people go to. When I first went to graduate school and met my research advisor and I negotiated how we would interact with each other and whether it was going to be timing-driven or interrupt-driven scheduling, because this is a normal thing that adults do. And so we decided on interrupt-driven scheduling, and then a little while later I found out I was supposed to be interrupting more often, which suggested to me it was actually timing-driven scheduling the whole time, and I was lied to. So don't make that mistake. It turns out you should bother your research advisor exactly every 168 hours, like on the dot. And that is, I think, also true if you're at your cousin's bridal shower, is one of the other things I learned. I have not that many cousins, actually. Okay, so I think it is much more theoretically interesting to think about, I'm going to say code, but I mean algorithms. It's much more theoretically interesting to think about code if something can happen between lines of code, during lines of code, concurrently with lines of code, and so on. When code is serializable, when it happens in one linear sequence, it can be interesting, but it cannot be as interesting. Right? That is fundamentally a lower level of complexity. So I like hardware interrupts a lot. Now, there is one thing I don't like about hardware interrupts, which is how many blasted lines of code you have to write to deal with them. And, that's in response to a good problem, right? But fundamentally, what I feel is that sort of hardware interrupts expose some limitations of basically using a text-based language to describe computer code. It's sort of like an awkward way to do it. Usually this is handled using the idea of like aliases and namespaces and function pointers and things like that. And so like it does work. The abstractions exist to support it. But it is odd. It feels awkward. Now, all of you attended Willamette University, which means you've taken CS151 and learned about the Portable Graphics Library.
How many people in here actually did?
And while you were learning about the Portable Graphics Library, which you all know about, because it is a required prerequisite for this class,
Yes.
you learned about things called event listeners. And event listeners are actually just hardware interrupts. So you're probably realizing at this point, oh no, you should be thinking this. Calvin can ask us to implement PGL in Rust bare metal for the final.
Oh no.
That's pretty bad, right? That's the worst thing I can think of. So I guess we should all try and stay on my good side, and I'll try and get enough sleep so I'm not crabby. Okay. No, I'm going to make you do Snake. I want to make you do Snake. I like Snake. Okay. These are not to be confused with software interrupts. And the reason they shouldn't be confused with software interrupts is because we're doing like a little bit of embedded stuff, right? And so it's actually going to matter how the hardware signals are actually reaching your device. And we'll talk about this a little bit. There is more than one piece of hardware in the world, but not for me. So a lot of times people talk about how computers can have something attached to them called a mouse. Have any of you heard of this?
Yeah.
So I've never used a mouse in my life because I'm hardcore. So I didn't actually know about them. But there's some slides that refer to these. I'm more of a cat person, so I only see cats around. So whenever I say hardware this week, I mean keyboard. Okay, I don't mean mouse. I mean keyboard. Specifically, I mean A through Z, 0 through 9, maybe space bar, and definitely no chords. So not capital or lowercase or anything like that. That's not necessary. Okay. We have to reset our context so we know what we're talking about. And in the process of resetting our context, we're going to have to review exceptions a little bit. Okay, so interrupts and exceptions, not the same thing. Not really different things either. They are both cases in which, and we don't have this metaphor fully filled out yet because we don't have any user level code. But so the operating system is hanging out merrily on its merry way. When it grows up, it will be running user space code, and the only user space code that you ever run on your operating system, Microsoft Excel, right? So it's running Microsoft Excel, the greatest piece of user space code ever written. And then all of a sudden, what happens is some human somewhere presses a key on a keyboard, or even worse, one of those Excel cells contains a divide by zero. These are two bad things. One of them is an exception that is caused internally in the computer by code that is running in the computer. The other is caused by a change to the environment. And then there are other examples, and we've dealt with the double faults and everything. So because we have some existing code in place to deal with this, you already have an interrupt descriptor table. And your interrupt descriptor table minimally includes a breakpoint exception handler and a double fault exception handler, and I probably have one of those here. Let's see if that's true or not. What do you think I called it? Like circ interrupts? Why did I type ls? So my brain this week has confused cat and ls every single time. I don't know if that's like a spring break thing. Like, I still know what CD and echo do, but, okay. So here's a version of an interrupts.rs. It contains a breakpoint handler and a double fault handler. Does all your code look like this?
No.
No. Should it?
Yes. Do you mean stylistically or?
Oh, yeah, does it have this functionality?
Well, mine does because I didn't do it.
Okay. Have you heard of keeping things to yourself?
It doesn't sound that very. It does sound very interesting.
Okay. So here, my double fault handler is firing, and my double fault my double fault handler is firing because I have an infinite loop. That's not true. It's not just an infinite loop. It's infinite recursion. The infinite recursion generates a new function stack every time. Because rustc does that for some reason. Do not attempt to defend rustc. Okay. The compiler couldn't look at this and be like, oh, hey, that's loop. Why does it not look at that and say, oh, that's loop? It's objectively loop.
Are you running any optimization whatsoever on it?
Okay, so tell me what to type. I'll type random things. Oh, we have to do release. Oh gosh, is it gonna work?
You ran it wrong.
Yeah, because
Spring Break is really...
I wrote... Okay, so fun fact, actually the only code I wrote over Spring Break is I have some pictures with watermarks on them, and I tried to take off the watermarks. That's all I did over break. I was like, I have a doctorate. I can figure out how to get rid of these watermarks. No, I could not. I got distracted so many times. Like I was baking cookies. I was stretching my hamstrings. I went for a walk. Do you know you can do that? So, like when you have free time. So Oh, so it does not appear to.
It should be. That's not even a Rust C thing. That's an LLVM thing. If C does it, so should Rust. It's not even a Rust C thing.
Okay, sorry. We can blame LLVM. That's fine.
I'm okay with that. It's everyone else in the class that would have a problem with that. Go ahead.
Okay. So anyways, I'm really not sure about Rust. Okay, you have an interrupt descriptor table. Now we're going to learn about double faults. This is probably a link to OS Dev. I don't know what it is. They're double faults, okay? You know what double faults are by now. Okay. This is the third week I've shown a slide that is inspired by this layout. On x86, there are about 20 different CPU exception types. And we sort of didn't really drill too deeply into why I was saying CPU exception types there, right? But here's the thing. A CPU and a keyboard, folks, those are two entirely different things. I have never used my keyboard to process anything centrally. And I have never used my central processing unit to bore any keys, right? So those are distinct. What this means is we have an itty-bitty problem. And that itty-bitty problem is, it's related to key value storage. There's a namespace collision. Because both the CPU exceptions and the hardware interrupts are numerically indexed, and they're numerically indexed to the same values, which is extremely, extremely cool. Okay, so now we're going to learn about interrupts. And to learn about interrupts, we're going to first learn about what they're not. Okay, you do not, under any circumstances, have to hand it to Blog, but you do have to hand it to Blog for this formulation. This is the correct formulation to understand interrupts. The alternative to interrupts is polling. What is polling? I write some code, and somehow I understand that there's some line of code that's going to run every so often. For example, I think it's going to run every 250 milliseconds. I don't know, maybe about that often. And every time that line of code runs, what it does is it sends some bits out into the ether to ask the keyboard if it has any keys depressed, waits for those bits to come back in, and then goes back about its merry way. Right? So that is a reasonable thing to do. It would be possible to write code that way, especially because the way we're writing our embedded code right now, there's already sort of a main loop that's running all the time. All we have to do is drop into that main loop. We currently don't have a way to sleep in there, so you probably calculate the 1000th prime number, then you read the keyboard, and then you calculate the 1000th prime number. This is not too hard to do. And we can give an example in real life. So I found out over break, have you all heard of apps? The things you put on your phone? So my phone is so cheap, I went to install an app on it, and the app said you have to buy a new phone. Which I am immensely proud of myself for this. I have been trying to get a phone that can't have apps on it for years, right? And I finally did it. Okay, and in addition to my phone not supporting apps, it seems like the ringer is anti-correlated with my current ringer settings, in that I have noticed it not going off after verifying the ringer is on, and also noticed it vibrating after I turn the vibrate off. I usually manage to keep it out of battery. Just this weekend, I saw it go through 18% of its battery in 80 minutes, which is a very, very high burn rate if you want your phone to be off, right? And then, in addition to it not working and having a dead battery and the ringer ambiguously working, I also usually don't know where it is. And that includes right now. So I don't currently have my phone on me, and I don't know where I left it. So, my cell phone cannot interrupt me. The only time I can get a text message is if I intentionally execute a line of code to find my cell phone, plug it in, turn it on, and attempt to get it working, because usually the screen doesn't also come on correctly, which is a really great thing. So this is really nice, for example, if your cousin's trying to invite you to a bridal shower in Lewisburg, but it's not as much of a feature if your cousin's trying to invite you to a bridal shower in San Diego, right? So sometimes you want polling-based scheduling, and sometimes you want interrupt-based scheduling. There's a part of San Diego called La Jolla?
Yeah.
Yeah, I think that's the part that I could be visiting instead of Lewisburg, Pennsylvania. Lewisburg? No, it's not. Okay, yeah. Okay. Yeah, La Jolla's great. It's almost as if they are the two most distinct places. Okay, this is the definition of polling. Okay. I think polling was used historically, but I'm realizing now that was just like word of mouth from people that like wouldn't have known. So I don't know if polling was ever used at all. Like maybe it was always interrupt driven, and I don't know. But anyways, it is possible to write polling based operating systems. No one does it. Okay. Here's an example of something that I know at least some students in my class do, because sometimes students that I am teaching, their cell phone interrupts me because I am not good at... Oh, gosh. I'm not good at anything.
I didn't do that on purpose, I swear to God. That's just
It would be so much funnier if it was on purpose.
Well, I can't keep things to myself.
Yeah, it was the negation of a keep it to yourself. Okay, so imagine you have a cell phone that you keep with you, charged, and with some way of notifying you that it has received a message. And so if you want to investigate this more thoughtfully, so along this wall here, so that like you go out and you like the wall on the left, the Civic Communications and Media major, they have some sort of like research project about like whether people keep their phones with them and like why they look at them and stuff like that. I don't know. Anyways, it's interesting. I actually got a bad grade in my mobile computing class in undergrad because I kept my cell phone with me so often it looked like I was falsifying data to show that my usage on my phone was so low. No one believed it. I just got a bad grade in that class because I'm committed to my bit. Okay, but so like, say you have a cell phone in class and it goes off, right? That will interrupt something. It will cause there to be a change of subject, and maybe the interrupt handler will be perfect ignorance, which is possible. You could write, for example, for the breakpoint exception, you could write a handler that executes no code and returns immediately. And actually, we can probably demonstrate that. I think we might be clever enough to do this. Source interrupts. I'm just gonna like comment out some lines here real quick. What I do wrong? I have to not return anything? Oh, because the panic doesn't return. Okay. Loop. Oh, no, that's not a loop. That's a loop. I think that's a loop. Does anyone know Rust? Oh, look, it didn't do anything. That's a possible interrupt. Now it did flush my hello world, but that's okay. I don't think that hurts anything. And again, what we changed is you can just have a handler that does nothing. That's allowed. Okay, so the examples of other. Why did I not capitalize the L in Lamborghini? I'm going to get sued by Lamborghini. Anyways, if any of you ever want to crash your Lamborghini into the classroom, we would not be able to have class that day. Something to think about, right? Yeah, that's crazy. Or worse, we'd have to have it on Twitch. Okay. Have you all been watching a lot of Twitch over break?
Watching a lot of Northern Lion on YouTube, but that's not...
Northern Lion. Oh, yeah. The Sisyphus guy, right?
The Sisyphus guy.
Yeah. Extremely relatable. Okay. So, computers are more fun if you can interact with them. According to some people, I guess I don't know for sure if that's true. it seems to me it would be reasonable to like write your code once and just like chuck it into the computer, and that'd be fine for me. But a lot of people really like the mouse. Yeah, you can just do endurance sports instead. They're kind of the same. I've learned this recently. I have this fun trick where I when people ask if I'm okay, I tell them I've gamified suffering. Yeah, that really kills at parties. Okay. Right? Yeah. It's like, I'm not suffering for no reason. I gamified it, right? Like, okay, so the kids these days, they love to play video games, right? They're all playing Slay the Spire 2.
Oh my god.
Yeah.
My dad won't stop.
Oh, so by
always on a Steam Deck every day.
by the kids, I mean your dad.
Yeah.
So your dad's always playing Slay the Spire, right?
52-year-old.
Which is multiple of 26. Pretty cool, right? I don't know why that's relevant. Was I doing 26 or something? Oh, it was marathons are 26.2 miles. It's an endurance sports number. Yeah, double marathon. Okay. So your dad's playing Slay the Spire 2 on his Steam Deck, right? We've all been there. And someone has to write an OS for the Steam Deck, right? And if that OS is only polling, then your dad will be unhappy because it'll feel like there's input lag, right? So you use interrupt-driven scheduling instead. Here's a claim that I don't believe. This is much more efficient because the kernel only needs to act when something happened. Okay, so here's my countervailing argument, right? Imagine a chore. So a chore I do is I like clean the dishes, right? We all love doing dishes, right? Can you do the dishes faster if you know you're going to do them? Or if, like, someone tracks you down and forces you to do them at a specific time when you weren't emotionally prepared, right? And I don't know, but I think it's at least worth thinking about that there should be some notion of a context switch cost. If every time someone hits a key, you immediately have to drop what you're doing, we know what it means to drop what you're doing. You have to write down the stack frame. You have to like cache all these registers to memory. You have to populate a new stack frame. Under some conditions, you'll have to like change which stack frames you're working with. Stack frame this, stack frame that. That stuff ain't free, right? And if you're working with polling, presumably you can write this so you're working with an existing stack frame. So I don't know. I'm unconvinced that it is much more efficient to use interrupt scheduling. I think people like it better because I think it feels better in your hands. It is sort of nice that when I feel myself pressing the L key, I see the L show up at about the same time. I kind of like that. But, maybe delayed gratification is good. You're all here in college instead of welding liquefied natural gas lines in North Dakota for $200,000 a year. So you have some form of delayed gratification to be here at all, right? Or you could be doing, what are the other fields that are hiring?
Arguably, this seems like more fun on the face of it than doing that.
Don't knock it till you've tried it. Yeah.
I spent the last 10 minutes proving that your code was wrong and that Rust in fact does optimize it.
So that's
the problem. What I'm saying is that it's your code, not Rust.
That's a great example of an interrupt, right? So we had the stack frame to discuss that, right?
Yes.
And then we changed context, and then there was an interrupt, and we had to reload a new stack frame, right?
So think about people preferring Jimmy streams.
Yeah. Yeah, see? So now Jimmy can make a stream about this, and then we can monetize it, right? I got demonetized.
Money for that,
Yeah. Yeah. Well, I think Jimmy gets all the money. It would certainly be unethical for me to sell your schoolwork, right?
That would be terrible.
That's what happens. I'm like, well, that doesn't mean it's not unethical.
There's quite a few. Are there a lot of universities that are
Especially
that they
art
own
schools.
all the intellectual property that's done by students for school?
You might be surprised to learn I have an opinion on that.
Wow, I really am.
Yeah.
So let me
It-
do that.
They were really opinionated on what my academic affiliation had to be on one of my papers a while ago. And I was like... anyways. Here's some quick life advice. Don't be like me. If I do it, just do the opposite, right? Like, odds are I'm doing the wrong thing at any given time, right? Okay, trade-offs, interrupts versus falling. Pros for interrupts. Probably fast. Now, if you pull at a high enough pull rate, it will still be perceived as faster because the stack frame change is not free. And then the cons can be disruptive. The biggest con here is actually probably an implementation side detail. So now that interrupt-driven scheduling is the standard, people have gotten pretty good at it. I suspect, well, in some cases I know, that many early privilege escalation exploits were basically just finding corner cases in the interrupt handler, and then you privilege escalate. Nominally, interrupts are less overall compute, which is really contraindicated with more overall complexity, because I think it depends on what you mean by compute. Perhaps it means like non-boilerplate compute or something. I don't know. I was not convinced by blog on this. Okay, so here is the hardware framework we're going to be working within, and I have some visuals here, and it's sort of important to see these visuals because we're going to actually use these visuals to inform literal lines of code we're going to write coming up. So we have something called an interrupt controller, and it's going to aggregate interrupts. What does this mean? Y'all remember the bus? Remember hopping on the bus? Yeah, we love buses, right? Makes a lot more sense to hook up an interrupt controller that handles all the hardware to the bus than to put a bunch of different things that can fire off interrupts on the bus directly. So it is common case to sort of decompose interrupts into an interrupt controller. That interrupt controller is incident on the bus. That bus is incident on the CPU. Then we can sort of just manage everything within there. The two types of interrupts I care the most about, which were helpfully also selected by blog, so I actually did not have to change what interrupts we were working with, but I was emotionally prepared to do so, are the timer interrupt. Think about this now for a moment. There's a little thing up here on my computer. This is managed by my operating system, and it tells me what time it is. It also tells me I'm missing a firmware update. But a lot of people don't know this. If you just click this little X, then that goes away. So you don't ever have to update your firmware. You can turn on Do Not Disturb. I don't know what that does. Okay, so this little clock up here. Nowadays, kids these days, everyone thinks everything's connected to the internet all the time, and you can just ask Google what time it was. Back in my day, Google wasn't founded yet, and so if you wanted to know what time it was, you had to pass current through a crystal and count how many times it vibrated, right? So me and my friends were there hanging out. We were counting how often the crystal vibrated, and it vibrated like a couple thousand times a second or something. I don't know how clocks work, right? Now everyone just gets a network update from the Atomic Clock in Boulder, operated by the NIST, National Institute of Standards and Technology, maybe. And so that's kind of cheating, right? That's a little bit too easy. But in the olden days, or perhaps if you like take your laptop to Starbucks and you're like boycotting Starbucks or unwilling to ask them for the Wi-Fi password so you don't have internet access, right? Somehow your computer has to guess what time it is, so it starts counting quartz vibrations again, right? So you probably have a timer of some sort. You have all seen time before because presumably you used like sleep or something like that ever. And those of you that took CS 151, which is all of you, have also written timer events, right, where an event happens every so often on the clock. Then there's also the keyboard, and then there's other hardware. Are we going to acknowledge what the other hardware is? No, absolutely not. Okay, it's not the mouse. That's what it isn't. Okay. So that's the idea of the interrupt controller, but perhaps in your mind you can imagine how you could make that with just wires and no sort of smarts to it. No microcontroller, no circuitry, well, other than the wires. You can implement it with wires only, right? It's much more common to use programmable interrupt controllers. And the benefit of a programmable interrupt controller is some of you may have at some point in your life plugged two keyboards into one computer, and the computer didn't like halt and catch fire, right? By the way, halt and catch fire, recurring idiom in computer science, and you now all know what halt means, right? Okay. So you plug in the second keyboard, it doesn't instantly halt and catch fire. Why is that? Because we have programmability. So it is the common case, and I suspect it is actually impossible to find a non-programmable interrupt controller. I have looked for hardware I've learned about physically. For example, I have specifically looked for an Ethernet, they often call it network switch. These things are wicked hard to find because you can do everything with a router, and it costs like $10 to make a router, so why would someone make a switch? Right? So you can usually get a specialized one from Linksys if you're like working in IT or something, but they can be relatively hard to find. I suspect it is equally hard to find a non-programmable interrupt controller. So, if you have a programmable interrupt controller, what can you do? You can change priorities. So probably the lowest indexed interrupt on your interrupt controller executes, it's not really executing, is regarded as having the highest priority. So if a timer interrupt comes in while someone is pressing a key, the timer interrupt pretends the key interrupt. The system has to process the timer interrupt first, and then it processes the key interrupt. This makes sense that you would want this to be configurable. So, we should also regard this as asynchronous. We've looked a little bit at asynchronity with exceptions, where we say, hey, an exception can occur potentially at any line of code. We have one slightly stronger claim now, which is that the hardware interrupts can occur during or between lines of code. So a line of code could be partially executed while the interrupt arrives. This doesn't really matter because execution is at such a rapid clip that we don't really care. But it is theoretically possible that you're imagining, like, if you had like a really sick jazz drummer or something, that person could successfully type the keyboard only at the upbeats on your system clock. And this would not affect anything, but it is physically possible. So, why does this really matter? I have thus... Where's my mouse? There it is. This is why you can never use the mouse. You can't trust it. Some of you are probably looking at blog, and some of you are probably avoiding it like the plague, and whichever one of those you do, I respect. The blog has taken great care to wrap all of its system-wide resources inside mutexes, and I have taken great care not to do that because it used spin locks, which I thought were stupid. And so that was fine until now. And now your code is like real sketchy all of a sudden. So I would encourage you to not worry about this too much. But it is true that it is now the case that something I avoided teaching you until now can potentially cause problems, because if, and I will show this in an example, you are concurrently trying to print text from a timer interrupt, and you are concurrently trying to print text from your main execution loop. Those prints are going through at the same point to the same resource, and there is no telling what order those characters are going to come out. Especially in the case of my print line, which does every character atomically. It can get really hectic and messy real quick, and perhaps that's unsupported. Here is a blog claim. Rust's strict ownership model helps us here with interrupts because it forbids mutable global state. And an example of the mutable global state it forbids is this static mute right here that we use all the time. So that is an example of something that we don't use. Deadlocks are still possible. And so a deadlock is like a Goldilocks, but it is the color of death instead of gold, right? So this would be like the singer of an emo band, right? It is still possible to have singers for your emo bands. When is that? If a timing interrupt is running concurrently to something else, if you are only permitting one user of print line at a time, deadlocks, okay, the timer could ask for a print line and print an infinite amount of content, and then the main executing system loop could never print. That could be bad. Okay. I'm hand waving right now. What am I doing? I'm saying, concurrency problems are for the networks class, tentatively scheduled 2028. Okay. We are going to learn about the 8259 PIC. And I'm pretty sure people say PIC for this. I've heard the term PIC before, and and I had a real job once, but it was a long time ago. So the AU259 is a common interrupt control API. Like everything else, when you're writing an operating system, you use like the first version from the 70s to get anything working. You're like, wow, this has a lot of limitations. Then you change it later. That's what we're doing here. We did that with BIOS. We did that with everything. So we're going to set up 8259, and it's going to be cool. Okay. This one has 8 interrupt lines, and then I think it also has like it's like a data and compute bus that go to the CPU. So anyways, many possible pieces of hardware converge into a small number of lines into the bus. That's what this thing is offering us. It was commonly the case that 8 things was not quite enough. So usually they would chain these together. So it makes sense if you have a programmable interrupt controller that produces a reduced number of lines that can go into a bus, that one of the lines coming into a programmable interrupt controller can itself come from a different programmable interrupt controller. So you have a primary and a secondary PIC. And the secondary PIC connects to one of the... so you have 7 devices and a second PIC incident on the primary, and then you have 8 devices incident on the secondary. Looks like this. I tried really hard to make this in something other than text, and I'm not super good at making graphics. So this is what it looks like. My eye naturally gravitates here to the keyboard. And so the way I'm thinking about this is I have a PIC. It gives highest priority to the timer, second highest priority to the keyboard, third highest priority to everything over here. So we have a separate real-time clock that is different from the timer. That makes sense to me. So I'm guessing there's a vibrating quartz somewhere maybe close to the processor, and then I have like an analog, or no, I guess a digital clock. Over here we have the mouse, because mice don't deserve rights. Then we have some serial ports. You all know what serial ports are because we've used serial ports for our serial print line, right? And then we got way down here, almost at the bottom, we got the floppy disk. And you all know what floppy disks are because you're under 70 years old. No, over 70 years old? You're either old or young, I'm not sure which one. Floppy disks are old. Okay. Each controller, well, they're port mapped. Basically, this is the problem. They're port mapped, and there's basically, they're called command and data, but there's basically input ports and output ports. So when I talked about bus, one of the ways we hand waved it is like, oh, you're just like throwing bits over the bus. Some of the bits say, hey, I'm asking for this device, and then some of the bits say, this is what I want this device to do. And some of the bits, for example, sometimes are a payload. So I can say, hey, AMMU, store this data, 37, right? The PIC has command line, which is the inputs that says, hey, PIC, I need to know what's going on at this location or something. So you can pull this thing. And then it can also interrupt. It can provide data ports, so it can push information up from a physical hardware device onto the bus and force the CPU to either read or ignore it. Now, these ports, by default, are, what is this? That is OX20, so that's 32 decimal, right? 33 decimal. That's some enormous number, right? 160 or something? 161, right? So there's just sort of built-in default expected port numbers. One of the problems with this sort of built-in default expected port numbers is that there are also, I'm not even going to say built-in default, there are hard-coded numbers within the CPU that correspond to certain exceptions. And we know these have to happen because exceptions are governed as the sole province of hardware at some point in their execution, right? So when a divide by zero happens, software is not involved until software resumes execution after the hardware has looked up a memory address in the interrupt descriptor table, popped that memory address, and begun executing code at that location. And it's usually also set up a stack first, right? So all that stuff happens autonomously. So we're not going to necessarily regard that as programmable because that is hardwired, not even hard-coded, right? So we cannot collide with these 20 different CPU execution types. So if we have some low-valued number corresponding to the data in command ports, we have to somehow change this. And the default picks are going to be attempting to propagate interrupts over 0 to 15. And these are colliding with CPU exceptions. So here's an example. 8, that's decimal 8. I guess it's also hexadecimal 8, but it's not octal 8, right? There's no octal 8. 8 is a exception double fault, but it is a serial port interrupt. So we can't just say 8. Any fun things to say about 8? There's the magic 8 ball. Taipei 101 has 8 collections of 8 stories. I ate some sandwiches before I came to class. Okay. What are we going to do? We're going to remap. This isn't that bad. So we're gonna take the programmable interrupt controller and we're going to say, hey, can you add like 32 to anything? And by convention we use 32. I believe this is decimal 32. The way to check is to write code and see if it works.
If the CPU stuff was hardwired, then why were the PIC numbers in that collision range in the first place?
So the PIC is from 1976,
Right.
and x86 is not, right? So not too surprising, and especially since it supports remapping anyways, I'd argue it like probably makes a lot of sense to start at 0 for all this stuff, right? It would be weird to have like a social convention where the keyboard is always like some large number. And another benefit is, so these are 32 indexed. In 76, you were fitting these addresses in 5 bits. So it makes sense to not go larger there as well. All that's speculative. I haven't like read any of that, but to me that all intuitively makes sense. Like, of course you keep the numbers low and then you remap them if you can.
That does make sense. Why then is the VGA buffer at like 8,000 something? Oh, because these things, that's a member.
That's virtual, right? Yeah, so that's not a real number, right? 8,000 is sort of like the name.
Right.
Yeah. So when I think that numbers matter are, for example, so like I think there's like the R9 register. It is the 9th register. That number matters because there are like literally 16 registers, right? There are not literally any number of memory addresses, right? So it is often good to choose arbitrarily large numbers, and I think this is the like social usefulness of like the hex dead beef. It's like, oh, it's a fake number that's made up and doesn't matter, right? We specifically want to choose a fake number that's made up and doesn't matter. In this case, we don't, because this is all actual wires that are incident on physical hardware, right? So we're numbering them literally. There's a crate that does this. What is the thing it does? It remaps the PIC and also uses the PIC. So, fun fact, this crate is not big. That is 108 lines of code. I believe, but I don't know. And I have my own idiomatic Rust expert, so I can verify this. I believe this is idiomatic Rust. One of the reasons that it might be idiomatic Rust is because it contains the impl keyword, which I would never use. It has some like unsafe masks and so on. We've got some and mute selfs. We're using U8s. So, you know, if you have any opinions about anything, you can take a look at this code and like look at some Rust, and I thought it was pretty understandable. Wait. Anyways, take a look at this if you care. I was very, very close to just assigning you to write that yourself because it looks pretty easy. And I sort of give you an option to write. There's a crate coming up in the lab and homework called PC Keyboard, and I definitely was like pretty far through writing my own before I finally turned the crate on, and I was like, I don't even know if this is easier, right? It's so few lines of code. Anyways, you all know and love crates, so let's go ahead and add a crate. I'm going to unfull screen, screen split, nvim cargo toml. I'm going to grab pick whatever. Going to exit that. See how big's my cargo. Ah! Okay, so So that's how big my cargo TOML should be. Now, if your cargo TOML is a different size, I won't worry about it because I think many of you didn't actually just name your OS Osiris, even though obviously naming your OS after the god of death is extremely metal. So like I don't know. Get it together.
You know what's even more metal? Naming it after the densest naturally occurring element, which happens to be a metal, osmium.
Naturally
metal.
occurring?
Densest naturally occurring, yeah. We can make heavier ones in particle accelerators that don't really actually exist.
I feel, yeah, I agree.
Osmium is denser than uranium?
Yeah.
Yeah.
That's weird. Oh, its boiling point is quite high.
Yeah.
What's it taste like?
Couldn't say.
Metal.
Flavor. Oh, the inflation has reduced its real value.
Damn.
It me. Okay.
This is
Very
another example.
poisonous. Very poisonous.
You can still taste it once.
Yeah.
That's only the opposite.
Yeah. Yeah.
Which
So
I'm assuming will form on the outside of it.
Yeah. And then you edit Wikipedia very quickly before you die.
They'll say that that's independent research and doesn't count.
so you need a collaborator.
Yeah.
Yeah.
Yeah,
You want to get on the ground floor of something big.
I think like there's enough of us in here. We could probably do a lot of research on osmium. Okay. So, what do you do with all of these things that you're glad are recorded? That's what I want to know. Okay. All right. So we're going to set up the programmable interrupt controller. I'm doing this in the thing I called interrupts, which probably actually should have been called exceptions until this moment. But the interrupt descriptor table is called the interrupt descriptor table, so like what am I supposed to do, right? Anyways, we're sort of following the loose, I guess the way I perceive it is that interrupts are the class and the exceptions are a subset, right? So anyways, I'm just going to go to the end of this file and I'm going to create a PIC heading, which stands for Prison Industrial Complex. What am I thinking about? Anyways, you should all read some Angela Davis. Okay, so we're gonna put some code in here. Here's some constants. These constants are useful because we want to refer to this. But let's go ahead and hit this up. So we're going to do a pub const pick one offset. So I'm going to do p10. That's going to be a U8. Why is it U8? Because this thing's prehistoric, right? So we're using U8s for everything. That's going to be 32. And no, it's not. It's going to be OX20. Then we're going to do another pub const. And this is going to be pick2. And that's going to be p10 plus 8. Why am I adding 8 to it? 8 interrupt lines. So I'm offsetting the second one by another 8. Then I'm going to make a public static mute. Why does this thing have to be public? I'm going to make it not public for now, and we're going to see what error we get. I'll call this pix, and I'm going to use a pick 8259 crate, and I'm going to use the chained pix abstraction. So what is the chained pix? They're chained as one is plugged into the other. So when we say pick2, we're going to provide these. And so this is going to be a way where the crate will handle programmatically remapping interrupt lines to numerical values that are not going to cause namespace collisions with this double fault right here, because this double fault would collide with a serial port. So I'm going to make a new one of these, pick 8259, double colon, chained pix. It does bug me a little bit that pix is lowercase, but that is following convention. Make a new one, and I'm going to provide p10 and, oh my gosh, I can't type, p20. Okay. Why is this unsafe? I actually didn't check if it was unsafe. It's probably unsafe. We are remapping memory. That should be unsafe. And I'm not going to do the thing where I put a space before my semicolons. Everyone hates that. Okay. Does this still work? Cannot find the value P10. Really? Oh, because I confused 1 and 0. Okay. So we've now, I still have a double fault. Oh, I should fix that real quick. nvim source main. I'm just gonna delete all of this actually. Okay. Cargo R. Wait, there's still a double fault? That's not great. Yeah, that's fine. Oh, I know where it is. Wait, why am I double faulting? Okay, there's a double fault in here somewhere. Oh, it's in the GDT, isn't it? It's like here or something. Sorry, I stun locked myself. Okay, there we go. All right, so we have tail source interrupts. We added this stuff in here. We've created a new chained pix. Now all we have to do is we have to set up handlers for it. Now, one of the things with setting up handlers for hardware is it's going to be weird. And it's going to be weird for all of it because the way each individual piece of hardware communicates with the bus and the CPU and so on is all going to be distinct. We have to take a brief aside here because we're now going to deal with the problem of mutual exclusion. It is now possible, as soon as you start doing things on timers, while separately doing things when the keyboard is pressed, that you try and write to the same memory location or read from the same memory location when you press a key and when the timer goes off. So you can possibly have inconsistency. Okay. This has not mattered until now. We are now about to enter the cool zone. We will deal with mutexes when we can do it properly, and not before then. The only way introduced in blog so far is spin locks, which are cringe and not at all cool. So we're not going to use them yet still, but we are going to deal with the consequences of not using them beginning now. Okay, I'm going to now initialize my prison industrial complex, okay? Where am I going to do that? To me, it made the most sense to do that in my established existing init IDT function. So I'm going to come in here, I'm going to add a new line, I'm going to pix initialize. And I'm going to assume that works, but I'm also going to test my code. And it does all of the expected goodness. This is how my double fault handler looks, so if you haven't done this yet, be advised. I think I don't currently have the you've done the homework assignment, so you have to initialize a new stack frame for your double fault handler. I don't currently have that set up in this branch of my repository, so that's what's going on. Okay. Now, the what's it called? The boot image, is that right? Its name is somewhere. The bootloader. The bootloader has been turning off interrupts when it turns on your OS. And why does it do that? Well, we're going to find out by turning interrupts back on and seeing what happens. So, let's go ahead and do this. Now, the way we're going to do this is we're going to issue a special command similar to like the in and out command and the halt command. So this is a very low level CPU command. It is not, it is below the level that code usually refers to. So the way we're going to interact with this is we're going to use the x86 crate, and we're going to do device-specific command. So don't run this on your AArch64, I think that's what they call it. We're going to use an x86 instruction. It is going to be an interrupt relevant instruction, and we are going to enable. That's not how you spell cargo. Carg-or is actually like a pretty cool name now. We could start a band called Carg, and we could be from Oregon. So, fun fact: as soon as you turn interrupts back on, you'll never guess what happens. You get interrupted, folks. It's incredible. This is like turning off your spam folder or something, right? So what's happening? We're hitting a double fault. Why are we hitting a double fault? Anything that comes in over the PIC right now does not have a handler. If it does not have a handler, it has to invoke the double fault handler as its handler of last resort. So any interrupt that is currently occurring will instantly go to a double fault. That's not scary at all. We've seen this before. We saw that with page faults, for example. So this is a problem we can solve, and we can solve it easily, super duper easily, by just beginning to write handlers. And we're going to begin with the first handler. And we know the first line coming in is the timer. And we now realize when we say that, oh, probably the timer is going off all the time. That's its job. And so, like, my alarm goes off every 24 hours because that's and I guess it goes off every 48 hours. That's like the frequency that I live my life in. Computers are much faster than me because they don't have to eat or sleep. So their timers go off more often. So what we're going to do now is we're going to track down that hardware timer. That hardware timer is now enabled. The timer interrupts are firing. They are triggering a response from the CPU. The CPU is attempting to invoke a handler. There is not a timer handler, so we have to write a timer handler so we avoid hitting the double fault handler. Absolute geniuses will notice that we can now do things using timers, such as implement Minecraft. Okay, so let's take a look at this little graphic. We got the timer. Timer is coming in very first index of the primary interrupt controller. So we can install a handler at that point. Now, I'm going to show you the code for this because I thought it looked kind of crazy. Rust always wants you to use enums instead of magic numbers. I guess that's basically fine. I really wanted to use constants for this. I think that would have looked atrocious as I added more things. So we're going to go ahead and make an enum. And an enum is really just giving names to numbers, but it's doing so in a specific context. And so we're going to give the timer, can I do interrupt? That's a lot of typing. The timer is going to be at pick 1 offset, which I called P10. And for now, we're just going to close that. So this is comma terminated, not semicolon terminated. Why is that? This is data, not execute. So it is not semicolon terminated. Okay, so I have that. We'll go ahead, cargo run this. And what do we find? By default, get this up, please. Okay, by default, when I create a public enum, it is going to use something relatively close to the default Rust integer type. iSize is not literally the default Rust integer type, but I32s are. So for some reason, this is signed. We are using hard-coded U8s because our programmable interrupt controller predates values larger than that. So we're going to have to specify somehow that we want our enum to hold U8s. And the way you do this is by specifying its representation. So I'm going to do that now. Octothorpe, Boxy Bracket, Reaper. See, I don't feel the Reaper fear the Reaper because I named my OS after the God of Death. So the God of Death would have higher fire authority over the Reaper. So I'm safe, right? So my operating system has made me immortal, which no mere metal can do. Okay.
Mercury.
Doesn't that make you extremely mortal?
If the emperors of ancient China have anything to say about it, yes.
Are any of them still alive?
I can't say.
How do we know? Do we have evidence that they're not?
Yes, we have.
All of them?
If I had been alive
What's
for
gonna be
2,000 years, I think I would have kind of withdrawn. I would have gone to live in Siberia and just sort of like checked out somewhere around the 1600s. Too much stuff happens.
Yeah, but now there's EDM, so wouldn't they be back?
Fuck.
Right?
Yeah.
Yeah. I feel like,
Maybe Mercury's bad for you. I don't know. Yeah. Shit.
yeah, it's worth considering. But just in this room, we have enough people, we can find out. If anyone is following along on this recording, I would like to note I am not recommending students drink mercury. Okay. So do not take this out of context and suggest. Okay. Rust, it's good. Yeah, I hated this. Okay. We're going to write a handler. And fortunately, I've already written a handler, so I'm going to engage in a little bit of yoinking. I'm going to yoink the breakpoint. Why am I yoinking the breakpoint? So the double fault handler, we've understood that's a special case. For example, it's diverging, right? So we don't really want to do that. So I'm going to start with breakpoint. And what I'm going to change about this is I'm going to change this to be the timer handler. I'm not planning on using the stack frame here. I can use it. Okay. And so we'll just change this to say interrupt timer. Interrupt timer. Oh, yeah, that's probably fine. I bet this will work. Oh no! Wait. Oh, this is okay. This is so weird. Two things happen at the same time, both of which are equally surprising to me. I'm still getting a double fault, even though I wrote a handler. So rude. And also, separately and completely unrelatedly, rustc, which I do not trust, is suggesting that the function I've written is never used. Perhaps those are related. And they're related in the following way. I have to add, so here in, is it set number? In lines, whatever this is, 8 and 9, we set our handler functions. We're also going to need to set our handler function for the interrupt timer, but it's gonna look awful. Okay, this is how bad it looks. This is like the worst thing you've ever seen in your life. So what's going on here? The static mute IDT, which is an x86, we can see it up here. It's x86 structures IDT interrupt descriptor table. That is an x86 and therefore architecture and therefore CPU specific interrupt descriptor table. Its abstraction does not inherently support the programmable interrupt controller, which is after all programmable and can be changed. So we are going to use this sort of, what's this syntax called? Like, I don't know. It's something you can overload with methods somehow and traits. I'm going to use address syntax to specify a location within the IDT, which is going to be the interrupt index. And I wrote interrupt index. It doesn't fit on one screen. Down here, interrupt index. I'm going to get the timer. Now, I am using this as an address, so I no longer want it to be a U8. I now want it to be a U size. We can just put it without a U size and see what the error is. And I'm going to set the handler function. And for some reason, we can abbreviate function but not handler. I don't know why that is. Okay. And I'm going to set it to be the timer handler. I bet this will work. Oh no! I expected a U size, so I have to change that to a U size. Jimmy, do you want to describe what's happening here with casting an enum into a U size?
You're turning it into a U size? Well, technically, it's taking it as a U8 because you added rep for U8 and then it's turning the U8 into a U size.
It's not saying it's taking it as a U8. It's saying it's taking it as an interrupt index, right?
Mm.
So, because it's a public
until you
enum.
say it as U size.
Yeah.
Until you try to say it should be a number, it won't interpret it as a number.
Yeah.
It's not a number. It's an enum.
Yeah, so it's a, maybe we use the term like language item. But the language item has an internal representation, and we can access the internal representation with...
When you use
Yes.
as, it accesses the discriminant of the enum.
Okay, there you go. So, yeah, I don't know. That's kind of interesting that works, but I guess I don't know why it wouldn't. Wait, is this going to work now? Oh, look. It's a timer interrupt.
That's nice.
That's pretty cool. I wonder what else we can do with that. What if I just don't print anything? Oh my gosh, folks. We can process timer interrupts and also have a working OS at the same time. And all we had to do, I'll cat it. All we had to do was comment out all of the text inside of our timer handler. Now, probably someday you'll want to do more than that in your timer handler, right? But today, that's pretty good. There is one sort of housekeeping thing we should do. I don't know why I did that. We're no longer using stack frame. Shouldn't I put like this here?
Why?
I want to put return there. That still works, right? Yeah, cool. All right. So, I don't know, like empty bodies of functions. Okay, so when you visit your friend's house and their dog runs up and barks at you, your friend was supposed to have trained the dog to instead like pick up a chew toy when they're excited and your friends come over, so that the dog doesn't bark and instead picks up the chew toy. Because it's easier to train a positive behavior than it is to untrain a negative behavior. So instead of writing empty function bodies to denote that I don't want anything to happen, I have the positive behavior of putting things that return nothing. Because I had to intentionally write the return statement so it's a form of self-documenting code. That's why I did it, okay? You can think of me as a dog barking at your friends, right? In real life, I'm actually much closer to a dog barking at the Rust C devs. Okay, in theory, the timeout sure should go off every so often. It seems to go off really fast. I do want to point out we only saw things pop up once. So let's. Okay. I'm gonna put another print in here. All right, but everyone be normal about it. Ah, it's me, a timer. Ooh. Okay. All right, close. Okay. No. Okay. My unwillingness to use is weighing heavily upon me. Ooh, it's me, a timer. Ooh. Real ones will note that it's a little bit odd that that overwrote Hello World.
Yeah.
Perhaps that's our first instance of two different resources trying to write to the same location at the same time. Maybe possible. I don't know. Could be. Actually, we can check. And the way we can check is we can do a new line before Hello World. Whoa, that's the wrong letter. So then they won't be in the same place. So in fact, I am overwriting it, which I can demonstrate here. If I print an empty line and then Hello World, first the empty line prints, then Hello World prints, then the timer fires. The timer writes to the first line because the timer and Hello World are executing at the exact same time, so they both check out the same location to start writing their text from. That is super weird, right? This should weird you out. This should stress you out. You should be anxious about this. You should want to learn what a mutex is and sign up for my networks class in 2 years. Okay. Just thought that was like maybe extremely cool. Okay. Blah, blah, blah. The timer only went off once, even though it fires instantly. How often does this timer go off? Okay. So the PIC expects an explicit end of interrupt signal from our interrupt handler. What is the usefulness of this? it does not make sense to reissue a timing interrupt while the previous timing interrupt is already being handled. So the PIC does not reissue the interrupt unless it receives news through its command port that the previous interrupt has been handled. This prevents interrupts from piling up, things of this nature. You know, it makes sense in some cosmological way, right? So somehow we have to issue a signal back to the PIC to say, hey, turn the timer interrupts back on. Otherwise, it'll just wait around. So we need to send this EOI signal. There's a handy built-in for this, and it is notify end of interrupt. So where are we going to do this? Let's see. Okay, I'm going to my timer handler. This is my timer handler. It's currently printing, it's me, a timer, ooh. And then it's also returning. I'm going to add a new line here. I'm going to enter unsafe. Why? Because I'm passing bits to arbitrary memory locations. So it makes sense this is unsafe. We're dealing with hardware. I'm going to go to my PICs, which is implemented as a static mute, which is itself unsafe. I'm going to notify end of interrupt. Interrupt index timer. And I'm going to turn it into a U8 this time because notify end of interrupt expects a U8 because notify end of interrupt is built on a PIC and the PICs expect U8 addressing. We're going to cast that to a U8. I'm going to close my various brackets. I'm going to cargo run. And I'm going to see my timers pop up. Let's do one slightly more interesting thing here first. I'm going to put a whole bunch of new lines here. I think that's 20. So I'm going to pop up my QEMU window. Hello World is going to appear in line 20, and then the interrupts are going to start from the top of the screen. Or are they going to start up there? So they're going to read the first line because they're going to check to see what the first line is the same time Hello World prints. And then they're going to start scrolling down and gradually overwrite something. So now we're actually going to get to see the overwrite in real time from two different resources working with the same memory. Okay, this is going to be relatively quick. So, it's me, a timer, and then it overwrites the Hello World. I'll show it again. Hello World. Oh, it's gone. Okay. So that's about how fast your timer goes off. To me, it looked like this fires about every 1/8 of a second. I don't know how accurate that is. You can decide that for yourself. Okay. All right. This works. Okay. I've demonstrated the race condition already. Well, we can make this a little more fun. D40L. Okay. That's not what I wanted to do. Okay, so I can print inside a loop. And when I print inside a loop, hopefully this looks vaguely interesting to us. We can see the timer is coming through sometimes, but not as often as Hello World in the infinite loop. So I can be trying to write to things at the same time. I believe I can also do a shorter timer message. Okay, what do I want to do here? Let's fix that. Timer. Source interrupt. I will just say time. I don't exactly know how these will overlap, but we keep the O world until we scroll off the end of the screen. One other thing I want to show you that's kind of exciting. So this is just firing timer interrupt. I'm now going to press any key on my keyboard. I'm going to do the J key. And look at that. It's a double fault. I wonder what that means. Okay. The main code loop, the timer handler, and the keyboard handler can all be executing simultaneously. So I say that, whatever's in start, whatever's in the timer. You can play around with this. You probably should play around with this. It's pretty interesting. We will need to deal with this someday. This is interesting and network and cloud relevant. Okay. All right. I want to show you one last thing in our remaining. I think we have 12 minutes left. Does that sound right to everyone? I'm pretty out of practice here. Okay. Now that we can have multiple things running at the same time, it is considerably less excusable that our main is looping infinitely. And it is engaging in gobbling, and specifically it is gobbling up available resources. So it is doing nothing, but it might be consuming CPU time, CPU energy, and in my case, hydroelectric power. Now, I don't actually know what optimizations are going on under the hood, so I would not be that surprised if Loop doesn't do this. But I was very surprised that recursion blew up the stack, even though Jimmy claims that's a problem with my code, which is objectively not true because my code did exactly what I told it to.
It's either your code or LLVM, and it's not Rust.
Okay, sure. Whatever. Wait, what did you use instead of LLVM to test it?
No, I looked at the LLVM output from Rust C, and Rust C is explicitly trying to optimize it.
Okay, so
So LLVM is doing something weird.
Rust C is detecting the infinite loop.
Yes.
That's interesting. Well, then it's neither of them, actually. That's a communications problem, right?
I mean, Rust is communicating to LLVM.
Yeah.
I don't know what LLVM. That's like what LLVM was supposed to do and be good at. So I don't know what's going on.
That's why I was shocked. This is like an aside, but this is interesting. Like, one of the things that convinced me Rust as a systems programming language is like I wanted to be able to write recursive code without paying the stack cost.
Yeah, you shouldn't.
Yeah.
I've done it before.
Yeah. And I'm wondering if it's. I mean, we're doing so much weird stuff with the bootloader. Like, who knows?
I wouldn't be surprised if the problem is bootloader.
Yeah. Okay. All right. So, anyways, we're going to try and quit our goblin. We're going to gobble less. We're like the opposite of a turkey. And we're going to replace these loops. Okay. And so we're going to replace the loop with a halt. So this is the halt and catch fire reference. Halt is another sort of like low-level computing concept. It's a hardware-level instruction or function. Same thing as in-out. Same thing as enable-interrupt. Right? And so having these loops here is a little bit counterproductive. We're instead just going to tell the CPU in CPU's own language, hey, hang around and don't do anything until an interrupt arrives. It's very easy to write. We're going to use an x86-64 instruction called halt. It's HLT because many of the instructions are 3 letters in length. And I'm just going to write this in my sorklib. So I'm going to nvim sorklib. I'll come down here. Ooh! I meant to do it after that. I'm going to create a public function halt. This function is going to be diverging. Why is it diverging? Because I'm telling it 2 things. I'm telling the programming language we're looping infinitely and are never going to return. And I'm telling the CPU halt. Now, I could theoretically be telling the CPU to halt an infinite number of times, but that won't happen because as soon as it gets the halt command, it'll stop executing. So I put the halt inside a loop, but the loop is for the language and the halt is for the CPU. So this is divergence between hardware and software. Loop x86 64 instructions HLT. Is there a tomato-like fruit that starts with H? Heirloom tomato lettuce? Wait, no. Bacon. Okay, so is there...
Instead, not an H.
Not an H.
Notably not an H.
Notably
Okay.
not like tomatoes either.
Okay, hold on.
It's
So,
food.
have you all heard of hempeh?
Yeah.
Yeah.
Tempeh.
Yeah, it's hemp-based tempeh.
That sounds gross.
So you can have a hempe lettuce tomato.
This is why I'm moving to the East Coast. Too much of this stuff.
There's annoying people on the East
Oh,
Coast.
for sure. Just like not like this.
I was exactly this annoying. So Weaver Street Market is on that coast. I know because it's in Carborough.
I don't even know that.
Which so Carborough, this is important, was the first municipality in the former Confederacy to have an openly queer mayor.
Huh.
Yeah, and that's the home of Hempe, which you have just slandered.
Was there a second?
Yeah, I think they're currently on the second.
Was there a second openly queer anyone in the Confederacy?
Yeah.
Huh.
Yeah, so Carborough and then Durham a few years later, I think.
Confederacy win?
No, queer win.
No?
Yeah. No, they're like mass producing gays down there. Okay. Wait, we're still recording?
Whoopsie.
I don't know if we're supposed to say former Confederacy or be like, the South! But, like, I know what it is. Okay.
Oh, that's what you meant. I thought you meant in the form, like during the Confederacy.
Oh, no.
Not
That,
just
I don't think
Southern
being
states.
gay had been invented yet then.
I
No, people were just like,
Was James Buchanan before or after?
I think you're right. I don't think. But no, it was around that time.
I think they were getting started.
It was around that time.
Uninvented.
Because, like, well, yeah,
Well,
like, yeah. Yeah.
Yeah.
It took, like, the idea of sexuality is, like, fairly recent, right?
Extremely.
Yeah.
We were talking about this in another class like a week ago.
Oh, okay.
Yeah, like, so, like,
we were talking in the context of like ancient Mesopotamia, but
yeah, which is, so I think, like, maybe, like, Joan of Arc was not trans while alive, but would be trans now, or something, like, I
Or
don't
like
know.
Kurt Cobain, yeah.
Yeah, whoever that is.
Whoever that is.
Is that
There's
Nirvana?
There's some speculation that, like,
Yeah?
I don't remember where it comes
Are you
from.
serious?
I'm not good at things.
Yes.
What were we doing?
not.
Okay, sorry, we're writing halt
Oh
loops.
my god.
Do I look like I know things? Wait, no, I'm the instructor. I know things. And I would also like to say for the record, I do not have a sexuality degree, so do not ask me any questions about any of the things I was just talking about. I do not know.
Or the Confederacy.
I will talk about the Confederacy, and then I will do that without a degree. Okay, Sork main. I'm going to replace loop with halt, but I have to do this really annoying thing where it has to be Osiris prefixed. What? Oh, did that not work? Oh, maybe it did. Really? Really? For real? For real, Zors? I have to specify that this thing diverges. Okay. Does that make sense? Does everyone know what I'm doing? Okay. This is the efficient way to do something forever. Oh, this should also be halt. I don't really know why you have to have a start in your lib. That was a little surprising to me, and I don't really want to know. Okay.
So halt makes the CPU stop executing, and it can get going again when an interrupt happens?
In response to an interrupt.
Okay.
It's like hitting snooze,
Gotcha.
which I never do because I always rise and grind. That's the end.
Would the CPU stop executing? It would just, like, if you were running a normal program and not an infinite loop, it would also just stop. You don't have to tell it to halt every time. If it gets to the end of its job, then it will also stop, right?
Well, in user level code, when it gets to the end of its job, it relinquishes control back to the OS, which
It does
manages the
some stuff,
CPU.
yeah. Okay.
So I think a helpful way to think of it is someone else had to write this halt loop in the OS that you're using,
Okay.
but you were relying on that under the hood the whole time.
Okay.
I don't think modern devices pretty much ever halt. They always have something to do.
Yeah.
They got to mine Bitcoin. They got to do sexuality research in the former Confederacy, like whatever.
Even if nominally even if there wouldn't be a halt, I think there's.
Okay, I'm going to open a private window and see if Abraham Lincoln was by, because I think he was.
Oh, like probably, right?
There's like an above 100%
There's
chance.
a good. I'd say there's a good chance. Well, there's a Wikipedia page about it, so that's kind of a flag.
Some historians. So there's another word for these people. We call them the haters, right?
Oh, he
Okay.
slept in the same bed as
His close friend.
Yeah,
They
they're
lived together for 4
best
years.
friends.
they were buddies.
So I'm pretty sure the Confederacy would have understood the idea of being gay.
Yeah. Yeah.
Yeah, they would have got. They would have figured. I mean, they would have different words for it.
They would have understood the idea of.
Here we go. A streak of lavender. Here we go.
Yeah.
That's what we
They wouldn't
had.
have necessarily said you are gay or you are bisexual or something like that.
A streak of lavender and soft